Dear students, welcome to today's lecture. Today's topic is the last topic in Unit 4, that is threads. So, threads are a most popular way to improve the application performance. How it will improve the application performance means via parallelism. See, when we divide a process into a number of execution units, independent execution units, which can run in a concurrent manner. Those are nothing but each execution unit is called as a thread. So they can run in parallel. So when the part of the code is divided into separate parts and they are running in parallel means execution will be fast. Okay. So in a traditional operating system, the basic unit of CPU utilization is a process. We will call it as a process. So for every process, there will be a program counter and the register states, which will program counter registers. Program counter will store the instructions of current execution and its own stack, its own address space will be there. But in operating systems which are having with the threads facility, one of the basic unit of CPU utilization is a thread. So these operating systems are described in this figure. Where there is in an address space there is only a single thread, so it is multi-threaded. So this type of single thread will correspond to the reveal or is similar to the traditional operating system. This is a multi-threaded process. In the address space we have threads. So each thread of a process will have a program counter. Like every process, each thread now will have all these program counters, registers, stacks, home stacks, all those will be there. In addition to that, all the threads of a process also share the same set of operating system resources. So, all the open files child process can use and the parent process can use, and all the sharing of the resources will be there among the threads. So due to the sharing of this address space, some protection will be missing between the threads of a process. However, we can implement the protection between the process between different users by using cryptographic mechanisms, and the protection between the process is needed as there are different users and they belong different processes belongs to different users. Many users will run different process. So it is not always owned by a single user. If there is only one process, it is owned by a user. So threads share the CPU time, and in the same way how the process will share the CPU time. So uniprocessor threads run in a time sharing mechanism in which each thread will run for few minutes and there will be a chance for execution of the threads for 5 minutes or 5 seconds, 10 seconds, like that, depending upon the algorithm they will execute. So in creating the child threads is also a very easy task, and at any particular instance of time a thread can be in several states like a process also. Similar states are running state, means a thread is in executing state, then it is called as running state. Blocked, if it is waiting for any resources, it can be in the blocked state or waiting state. for it is if it is waiting for either resources like that. And ready means the process already gathered all the resources and it is waiting in the ready queue, then it will be in the ready stage waiting for the CPU time, or it can be in the stage of termination. When the process when the thread execution is finished, it will reach to the termination stage. So due to these similarities of the threads, these are all often viewed as a mini processes also. For what? Why? Because every process will have these features. So these are very much similar to threads. So an operating system with this thread facility, where a single process corresponds to multiple threads. But in traditional operating system, a single thread corresponds to a single process. So threads are often referred to as a lightweight process, and the way how the process will execute in traditional approach is considered as a heavyweight process. So why there is a movement towards threads means what are the motivations for using threads? So creating a new thread is much simple, and within a process we can easily create a new thread. So switching between threads will share the same address space and is considerably cheaper than switching between the process, and it will have its own address space. And threads allow parallelism, whereas process do not allow parallelism. Means we have to run line by line the code, whatever code it is there, we have to run line by line, and it will be executed by a single thread itself. But here we can threads will allow parallelism. Unit of execution unit will be different, and we will run it parallelly. When the whole code is divided into separate execution units, then obviously it will improve the performance. So it is another motivation to use threads, and resource sharing also achieved more efficiently and naturally between threads of a process. So, so a thread is nothing but an execution units of a process or a one process. So what are the different models of organizing threads? See here there are basically three types of models. Those are dispatcher worker model, team model, pipeline model. What are these models for organizing threads? Means how threads can be organized. Uh, Depending on application needs, means one application requires some type of resources, another application needs will be different. Both will not match. So the threads of a process of the application can be organized in different ways. In order to meet the needs of the user, threads can be organized in three different ways. The first way is dispatcher workers model. See here, a server process for processing incoming requests, and all the requests will be handled by the server process, and it will process the incoming requests and it will dispatch to each thread. So here this process consists of a single dispatcher thread. This is single dispatcher thread, and multiple worker threads will be there. This dispatcher thread will accept the request from the clients, and after examining the request, what type of request it is, like that after checking that request, it will dispatch the request to one of the free worker threads. These are worker threads. But if this worker thread is be free, then the arrived request will be given to this worker thread. Each worker thread will work on a different client request. Client 1's request, client 2's request, client 3's request, like that. Each worker thread is responsible for running different clients request. So therefore, this multiple client requests can be processed in parallel. So this is an example of this model in which dispatcher means dispatching, dispatcher workers model. So there will be one dispatcher thread and many workers thread. The dispatcher thread will dispatch the work or any request from the client to the free worker node, worker thread. These worker threads will run different clients request. So they can run in parallel. But this type of dispatcher thread is like this, used like this. And the second is team model. And in this model, these all threads behave as equals in the sense that there is no dispatcher here. So there is no dispatcher worker relationship here. So each thread gets and process client requests on its own. Each thread is responsible for getting the request from the client and processing it. Each thread of the process is specialized in servicing a specific type of thread. Means this one is specialized in calculations, this one is specialized in analysis, like that. Each one will have a specific type of request and they are specialized in it. So multiple types of requests can be simultaneously handled by the process. So here incoming request that may be of three different types. Each request type will be handled by the different threads. That is team model. As a team, they are solving different types of client requests. And the next is this one, pipeline model. So in this type of organizing threads, this model is useful for applications which are based on producer-consumer model. Means whenever the producer is producing the items, consumer should consume them. Like that, where there is in which the output data generated by one part of the application will act as an input for another part of the application. See here, the output generated by this thread will be acting as input to the thread. So this thread's output is acting as input to the third thread. Like that, they are organized in a pipeline so that the output data generated by the first thread is used for processing by the second thread. The output generated by the second thread is used for processing by the third, and so on. We can build the output in a pipeline. So final output of the process to which the threads belong will be given by the last thread. Okay. This is the pipeline model. Issues in designing a threads package. So the first issue in designing of threads is thread creation. Threads can be created in two approaches, that is in a static approach and dynamic approach. We will see first the approach of static. So here in static approach, the number of threads for a process will remain fixed for its entire lifetime of that particular process. Means the number of threads for a particular process is fixed and it cannot change in static approach. While in dynamic approach, the number of threads of a process will keep on changing dynamically. In this approach, When a process is started with a single thread, new threads can be created and when needed during the execution of the process. Means here we will decide how many threads are required for running that particular process before starting of the execution, and it is fixed. But here it may start with single thread and it can create any number of threads as and when required for running that particular process. Okay. So in static approach, all the it is a fixed stack and it is allocated to each thread. The stack size of a thread is varying in dynamic approach. So first issue in threads package is thread creation. Thread creation can be created either statically or dynamically. In static approach, the threads of a process will remain fixed. It means we cannot change the number of process, means to increase or the threads or to create new threads or to terminate the threads is not possible. While in dynamic approach, the number of threads of a process keeps changing dynamically. We can even start with a single thread and new threads can be created whenever required during the execution of the process. And a thread may destroy itself when it finishes its job. Means a process is divided into 4 threads, and if thread 3 job is complete, it can also destroy itself after finishing that job in a dynamic approach. Okay, and the next issue is thread termination. Threads termination of threads is performed, which is same as the conventional process. Means how we will terminate the process is similar to the termination of the threads. So a thread may either destroy itself when it finishes its job, means after completion of its running process, it can destroy, so that by using an exit call, or to be killed by from outside any command which specifies the thread termination, then the threads will be terminated. In many cases, threads are never terminated, and we have to uh, terminate or kill that all the threads. Okay, all its threads are created immediately after the process starts up. So in thread life cycle also we will have a stage called as thread termination. And the next concept is threads synchronization. So here all threads will share the common address space, so some mechanism is required in order to prevent the multiple threads which are going to access the same data simultaneously. This one we have discussed in our synchronization concept also, where the address space is shared by more number of processes. In such a case, we need to prevent multiple process entering into the critical section. All those we have discussed. The same is here, but the concept will go with the threads. That's it. So a segment of code in which a thread may be accessing some shared variables, that region is called as critical region, right? We have discussed this one, like when two or more processes are sharing the variables from a segment of code from a memory area, it is called as critical region. And we have also seen about the mutual exclusive access, and here also we will have one mutex variable which is called as a binary semaphore. Binary means it consists with two states. Those two states are locked state or unlocked state. So for achieving this thread synchronization, we are using one mutex variable which is called as locked or unlocked state. whenever a thread wants to execute the code in the critical section, it performs a lock state, means that lock operation will not allow any other thread to run into the code which is there in critical section. The lock operation, after completion of that lock operation, the mutex variable changes to unlocked. So at a point of time there will be a locked state only for one thread. The thread is blocked and entered in the queue of threads waiting for the mutex variable. Whenever any thread is blocked and it is entered into the queue of threads, they will wait for the mutex variable. After getting that mutex variable, they will go to the lock state and they can run the critical section code. And a status code indicates about the failure is returned to the thread. Okay, so these are the lock and unlock operations. Mutex variables are simple to implement because they have only two states, that is lock and unlock states. For more general synchronization requirements, the condition variables are used. Those condition variables are signal and wait and signal. So these two are operations normally provided for condition variable. When a thread performs some wait operation on a condition variable, then the associated mutex, what we have discussed earlier, the associated mutex variable is unlocked and the thread is blocked until the signal operation is performed. Okay, after getting the wait, that is in the blocked state until it gets the signal operation. This signal operation is performed by some other thread on the condition variable, which indicates that the event being waited. It is waiting for the occurrence. So when the thread performs a single operation on the condition variable, signal operation on the condition variable, the mutex variable is locked. So this is the mechanism shown here. Lock of mutex A means it has acquired that mutex lock. It succeeds. It runs the mutex A runs the critical section code and it unlocks the mutex, means it want to get out of that critical section, and again it gives the signal A is free. Like that, lock mutex A, wait of A, thread 2, it is in the blocked state. Whenever that A gets the lock of mutex A, it is succeeded. Okay, it is an exclusive use of shared resource A. Here a free is a condition variable for resource A to become free. A has to wait, and we will have the thread scheduling concept. So the next issue is thread scheduling. A thread can be scheduled in variety of ways, means by using different scheduling algorithms we can schedule a thread. So this is one of the important issue in design of the threads package. How to schedule the threads, means which thread should run first, or all the threads should given priority at the same time, or all the threads should given the CPU time at the same time. Like that, how to schedule the threads is nothing but the thread scheduling. So an application programmer can use the heuristics of this problem to decide the most effective manner for scheduling. All those scheduling policies will be taken care by the designer of that algorithm. So some of the special features of thread scheduling which are supported by a thread package are priority assignment scheduling. Means this is one of the simple scheduling algorithm in which the threads are scheduled on first in first out basis or round robin policy basis, and it is used to take the CPU cycle. See here, every time the threads want to execute, then it should get the CPU cycle time. CPU time, if in CPU time only they can execute its block of code. So by scheduling, thread scheduling scheme may provide some flexibility to the programmer. Why? Because to assign priorities to various threads of an application will ensure the important ones will run first. Okay, means thread 1 and thread 2 are there. Out of thread 2 and thread 1, thread 1 is of high priority job, then it should be given much more priority, higher priority than thread 2. In such a case, thread 1 will run first by suspending or by pausing the job of thread 2. Like that, priority assignment will use these algorithms, and priority based thread scheme can be both preemptive and non-preemptive. Means non-preemptive means if we are running the thread 1 until the completion of thread 1, we will not allow any thread to run the job. Sometimes if thread 1 is having high priority and it is non-preemptive, then thread 1 will only run until its completion of its work. If even any high priority thread approaches also, then it has to wait, as the thread 1 is of non-preemptive one. That is non-preemptive scheduling. Whereas in preemptive, thread 1 is executing. If thread 2 of high priority is approached, then thread 1 process is suspended and thread 2 will be going to the running state. That is priority based scheduling scheme in both preemptive and non-preemptive approaches. And the next is the flexibility to vary quantum size dynamically. Okay, quantum size dynamically means here a simple round robin scheduling scheme will fix the time quantum. Means quantum is nothing but the time how many seconds a thread can run its program is nothing but the quantum. Say for example, instead of giving priority, what we will do in round robin, all the threads will get a time quantum of 4 seconds. If this thread is want to execute 5 seconds, it will execute 4 seconds, and then the turn will goes to thread 2, it will execute 4 seconds. If it wants only 4 seconds, it will execute that job in that particular first run. Now again the turn comes to thread 1. The leftover job is only 1 second. So it executes in second run, and it again gives the turn to any other thread. Like that, for certain quantum time we can execute the threads, and those threads will be executing for fixed length time quantum. It will be fixed first itself. So the size of the time quantum will be given to each thread. So it can vary depending upon the size. Quantum size will dynamically change. So handoff scheduling means in this scheme it allows a thread to name its successor if it wants to. Means after sending a message to another thread, the sending thread give up the CPU time and it requests the receiving thread to run next. This is handoff scheduling. We are handovering to another thread. Okay, that is handoff scheduling can enhance performance if it is wisely used. And the next is affinity scheduling. This scheduling policy will be used for further performance on a for better performance of a multiple multiprocessor system, and this is nothing but the affinity scheduling. What we will do in this scheme is a thread is scheduled on the CPU and its last run will take part of its address space will be in still CPU's cache. That is affinity scheduling. And the next is signal handling issue. Means when we have to generate any signal, the signals provide the interrupts and exceptions. In that concept of synchronization, wait and signal approach we have seen. Like that, signals will provide the software generated interrupts and exceptions. Interrupts are nothing but disruptions, and they can stop the execution after receiving any software interrupts, whereas exceptions are caused by the unusual conditions. Any during the thread execution, any exception like a division with zero or any bugs in the logic will give you a error and exception. So these two main issues are associated with handling these signals, and these can be handled in using threads. So we have to create, set and read these uh, all issues in designing a threads package. And the next is implementing a threads package. So there are two approaches for implementing a thread package. It can be implemented either in user space or in a kernel approach. So these two approaches are referred to as user level and kernel level. What in user level approach means, the user consists of a runtime system, and that is a collection of all the threads, and it manages the routines. So threads run in this user space on top of the runtime system, and they will be managed by it. Okay, top of the run system. So all these procedures are given here, which is illustrates about the approach of kernel user level, that is process and threads will run here, and this is the user space up to here, and this is the kernel space which maintains the process state information. Above the kernel, runtime system is there, and it maintains threads status information. Above here, the user space, the process and the threads will be maintained. So here in this approach, the existence of the threads are not visible to the kernel. They are invisible to the kernel. The kernel functions are very much similar to ordinary kernel, and it manages only single threaded heavyweight processes. SunOS 4.1 will use this approach. And the next approach is kernel level approach. There is no runtime system environment here, and it is used, and the threads are managed by the kernel itself. So therefore the threads status information table will be maintained in kernel itself, and all the calls which will block a thread are implemented as system calls, and those calls are used in the kernel itself. Even when the thread blocks also, the kernel selects any another thread to be run. So the existence of threads is known here, and the kernel can know how many threads are there, and it uses signal level scheduling approach. So this is the thread maintains the threads status information, but here it will maintain the process status information where it can be considered as a single process, and all those processes will be that process is divided into multiple threads, it will take care. Runtime system will take care. But here the kernel will only takes care about the thread status information. So the advantage of this using a user level approach is that it can be implemented on the top of the operating system, which does not support threads. So kernel level approach, it is not possible. Why? Because the operating system should support the concept of threads. In user level approach, we can use the two level scheduling, and the users will have some flexibility here, but here we will have the single level schedulers. And the next concept is thread management. So, threads management. How to manage the threads and the library procedures which are associated with DCE threads. So the C threads package was developed by Mac operating system, and it is a lightweight process, and it was proposed by Sun OS. So DCE threads will maintain the threads package, which will have the multiple number of library procedures, and those library procedures, using this library procedures, we can use the threads and manage them in a very good manner. So DCE is nothing but it stands for the distributed computing environment threads. Distributed computing environment threads. This is distributed computing environment threads, shortly called as DCE threads. So this one is threads management, and what are the different uh, procedures we have in threads management? Means p thread underscore create. This thread, this one is used to create a new thread in the same address space as the same calling thread. And all these are, a package will consist of different classes, interface, and all the libraries will be holding in a package. Like that, in thread package also we will have this pthread create exit, means to terminate the calling thread we can use this routine, and this routine is called by a thread itself. The thread itself can call that routine, and it can call that routine whenever it thinks that the job's execution is finished. By itself it can terminate by using this routine. And the next is pthread join. Here it is used to cause the calling thread to block itself. Until what time it will block? Until the thread specified arguments are routine arguments are terminated, it will be in the blocked state. And detach is used by the parent thread to detach from a child thread. Okay. And pthread cancel, it is used to kill another thread. So whenever any thread want to kill any other thread, if T1 calls on T2, then T2 thread will be killed. That is pthread cancel. And set cancel, this is used by a thread to enable or disable the ability of other threads to kill it. Means here we are killing T1, T1 is killing T2. So if we don't want to do like that, we can use this procedure to set cancel. Means in such a case, no other thread can kill any other threads. No thread can kill any other threads. That is this. So these are the package routines which will be used while using threads. And the next is thread synchronization. Means this DCE threads package will provide support for the both mutex variables and conditional variables, which we have discussed earlier. Mutex variables are used when access to shared resource is there, and condition variables are used with the mutex variables in order to allow the threads to block and wait. So here DCE threads package will differ, and it supports the following types of mutex variables, that is fast, recursive and non-recursive variables. And the next is this one. This is about thread synchronization. That mutex init is used to create a mutex variable. Destroy can delete a mutex variable. Mutex lock, as it can achieve the mutex lock, it is used. And conditional init, condition variable it is used. Can be variable destroy, variable wait, variable signal, and try lock. Broadcast means whenever any thread is free and it is want to wake up all the threads waiting on this condition variable, then this one is used, thread forms. So in thread scheduling, next concept is thread scheduling. In this we will use about thread scheduling, which we have discussed in short in this lecture only. The DCA threads will support the priority based thread scheduling we have discussed. So it allows users to specify not only the priorities for an individual thread, but also the scheduling algorithm can be used for those important threads. So scheduling algorithms can be of these three types here discussed with. First in, first out, means whatever the thread comes first, it will be given the execution time. So that one is here. The first thread of the first non-empty highest priority queue is always selected to run, and the selected thread continues to execute. Here there is no preemption in FIFO, and this algorithm will suffer from starvation, means if any low priority thread arrives, as it is choosing the highest priority out of the ready queue, if there are T1, T2, T3 are there, and T3 is having highest priority out of the queue, T3 is selected and it will be executing its job. If that thread is continuing for much time, then the lowest priority threads will be on keep on waiting for executing its 2 seconds job or even 4 seconds job. It need to wait for 10 seconds in order to complete the highest priority job. Okay, it is nothing but when highest priority job is executing for much time, even if any thread arrived before that thread and it is having the low priority, may lead to starvation as it is not getting chance to execute its job. And the second scheduling is via RR, round robin. So here we will be given the time quantum, and fixed time quantum will be using, and it will be given, all the threads will be given equal importance, and it runs each thread for a fixed quantum. I have said this one also in this lecture before itself. If you have missed it, listen there. Round robin, where there will be a time quantum, and every thread, if there are three threads, it will execute for three threads, and the time quantum is 5 seconds. All the three threads will get 5 seconds, 5 seconds, 5 seconds of time. Further, any remaining of the job is left, it needs to execute it, wait for the second chance. Another in the second time, some jobs may be some jobs execution, some threads executions may be completed. In such a case, if that time will go to the third thread. Like that. This algorithm may also cause low priority threads. And the default is this one. All the threads on all the priority queues are run, and one after another, using a time sliced round robin algorithm. So to select a scheduling algorithm of this choice, P-thread set scheduler, all these are used to select the scheduling algorithm. Out of these three, we can schedule. We can get the currently used algorithm via get schedule. Set priority used to schedule priority of a thread. And no, to get priority means what is the priority of that particular thread can be get by get priority. Okay, and I hope you all have understood this topic. Thank you.